This is our first video on ballistic pendulums. Why in ballistic pendulum problems can we not use energy conservation exclusively? That is, why at some point must we use conservation of momentum? And the answer to that is that in a ballistic pendulum problem, there is always a totally inelastic collision, and mechanical energy isn't conserved in those. So we have to use conservation of momentum for that part. In a ballistic pendulum problem, typically you have to use conservation of energy as well as conservation of momentum. So let's do an example. Here we have a bullet approaching a block of a ballistic pendulum at an unknown speed. So that is what we're after right there. The bullet embeds in the block, and then the block swings up, as you can see here depicted in the picture. So this bullet is going to thunk right in there, and that's going to cause this ballistic pendulum to swing up. And so what we've got here is we know the mass of this block. We can measure the angle that it swings up through. We know the length of this, and we know the mass of the bullet. As often happens with ballistic pendulum problems, we're going to work backwards with time. So let's find the speed of the combined mass at point 2, which is right there. What we're going to do between point 2 and point 3, we're going to conserve energy. That's where we're going to conserve mechanical energy. And this mass right here is going to have kinetic energy. So the kinetic energy at point 2 is going to equal the gravitational potential energy at point 3. So let's see if we can do this. 1/2. Now what's the mass going to be? The mass is going to be the bullet plus this block, which nicely comes out to be 3 kilograms. And that has some initial speed. I'm going to call it V combined when the bullet and the block are combined. And all of that will have turned into gravitational potential energy, which is going to be m times g. Now, what's h? H is the height to which this has risen. And if we look at the dimensions here and we look at the angle, it looks like between here and here, this length is 4. So 4 times the cosine of 60 would be 2 meters there, which means the block has come up 2 meters as well. So this height right there is 2 meters. So that's what I'm going to put right there. The 3's cancel out right there. We're going to get the square root of 40. I got the combined mass right as it starts to swing upward is going to be the square root of 40, which to 4 significant figures comes out to be that. And I'm only leaving it like that because we might need that number later on. In fact, we will. We're going backwards in time. Now we're going to go from case 1, which is right here where the bullet is by itself, into case 2. That's a collision. That is a perfectly inelastic collision. And as we know, energy is not conserved in those, but momentum is. So we're going to conserve momentum in that case. And the initial momentum needs to equal the final momentum. This is all in the x direction right there when those two collide. So the momentum to start with is going to be 0.05. That's the mass times the v of the bullet, which is what we're looking for, and that needs to equal the mass that is moving at the end, which is the block and the bullet together. And we just found that those are going to start swinging with that speed right there. This number comes out to be, doesn't that look like roughly 19 or so? And then we're going to divide by this very small number. You'll need a calculator on this, probably. I did. And that comes out to be about 380 meters per second. So that was the speed of the bullet before it hit that block. Now let's determine the amount of internal, or basically thermal energy, generated from this collision. So what we're going to do is we're going to find the kinetic energy initially, we're going to find the kinetic energy at the end, and we're going to subtract those, whatever the difference is. So initially, before things started, we had just the bullet moving, 1/2 mv squared, just the bullet. Right after the collision, the mass that's moving is the block plus the bullet, which we've said has a total mass of 3, and their combined speed right there from the get-go was 6.324. So the total amount of kinetic energy that we had to start with comes out to be about 3,610 joules, and after the collision we only have about 60, which means the thermal energy that was generated in this is the difference between these, roughly 3,550 joules.